Hi everyone. So this is Midas, microcluster based detector of anomalies in edge streams. So this work was published at AAAI this year, and it is joint work with my advisor Brian and Minjin Christopher from Carnegie Mellon University, and Kijun is from KAIST. So let's proceed. So we all know like there are a lot of DDoS kind of attacks, intrusions, and these are happening even in big corporations like GitHub, and like there was a Twitter attack recently. Several bitcoins got stolen. So and it's happening with even high-profile users. So like even though Twitter, GitHub, these are like some of the most secure companies out there, still such kind of attacks are happening, and they're very easy to detect because like even these are actually like bot kind of attacks, so they're very easy to detect even from a human user. So like machine learning should definitely be able to do it much better. So like that is the motivatory application behind this. And for intrusion detection, we can just like see this as an example where there are three malicious or anomalous users who came in and they wanted to attack like all these normal users on the top, and they sent a lot of spurious or suspicious edges and communications. So we want to detect this kind of sudden behavior where a similar group of malicious or anomalous entities come in, and they're throwing like suspicious edges or communications, and this is the scenario which we want to detect. So we are working with time evolving graphs. Time evolving graphs are everywhere, like computer networks or your instant messaging kind of networks like Twitter, Facebook, and you have like a user product kind of graph for Amazon and other things. Wherever there is a time evolving or a dynamic graph, and you want to detect anomalies there or the malicious entities which are acting abnormally. So all those kind of things when you want to detect, so Midas can be applicable there. And so the scenario which we're considering is an edge stream. I'll go into the details of like what are the different possibilities like after a little while. But an edge stream is when you are receiving an edge at each time instant. Like you can receive multiple edges also at the same time instant, but modeling the same graph, the same example as an edge stream. So we have U1 to U6 as the normal or the like good people kind of users, and A1 to A3 are the anomalies or the malicious entities. And we observe that A1 to A3 come in a very short span of time. For this particular example, they arrive at the same time instant as 6, but like they can arrive in a very short span of time, and we want to detect this kind of anomalous behavior, and we want to do it in real time and as soon as possible. So because like the lag between their arriving and their detection, so that is when the most of the harm is done. For like example, in the Twitter attack, so most of the money got stolen because like this couldn't be detected very soon. So if something like this can be detected as soon as possible, and even better if it can be detected in real time, so that is like amazing, and that is what our goal is in this particular work. And so the roadmap of the presentation, like we'll first formalize the problem setting, what we were wanting to do. Then I'll discuss the two algorithms or the approaches which we have in the paper, and the how the related work spans in this area, and the experiments and how we're kind of contributing this, and how the future is going for this particular open source project, and what all happened in the community. So we'll discuss that. So the problem setting is that input is an edge stream E, and like the graph is a time evolving graph. So that is the input, and the graph can be directed. It is multi graph, so there can be multiple edges between two nodes at the same time instant as well. And it is like we're handling discrete time instants, so that like we can know that okay, this edge arrived at this particular time instant, and we'll be giving as an output an anomaly score for each edge. So for each edge, like in the graph, we'll be giving an anomaly score there and then. So that is what our goal is. So the contributions for this particular work were that it detects microclusters. It gives like guarantees on the false positives, like what are the false positive probabilities. So for critical applications, this is quite crucial, because you want like a guarantee on your false positives. You do not really want those to extend beyond a certain limit. And any streaming or an online algorithm, we want the memory to be constant, like constant update time and constant memory is like really like like a necessity for a streaming algorithm, because we cannot have afford unbounded memory in a streaming algorithms, because we don't know how many nodes will keep on coming later. So we want our update time and our memory for like to be constant for each edge. uh, so yeah, let's go into the algorithms. And so Midas, first we'll just like briefly discuss like the background. So for this particular case, there can be a lot of time series based methods. So in an offline scenario, like this problem has been quite well explored, but in an online scenario, the memory is bounded and the set of nodes is also not fixed. So we want something else. And the naive solution for this particular problem is that we can assume that our entire distribution is Gaussian. So if we assume that the entire distribution is of the past is Gaussian distribution, so for that we'll just compute our likelihood at this particular point at the current time instant, and then we just manually see, okay, if the likelihood is lesser than the threshold, we declare it as an anomaly. The problem with this particular assumption is that we are assuming that our entire past is following a Gaussian distribution. So that is not what happens in real life. So you cannot really make that strong an assumption. So we make a weaker assumption where the mean level of the past is the same as the mean level of the current time. So we assume, suppose you had 1,000 edges and 10 time instants. So we just divide it in the normal ratio 9:1, which is 900 is to 100. So our past is 900 edges and like our current is 100 edges. That is our expected value. And we observe 0 and 1,000. So we can easily see like something like this is an anomaly. So if you carefully see the graph, like intuitively, if you just want to understand this problem, so the difference between the occurrences and the expected value. So if your occurrences is like really huge and your like and the expected value was very low, so the anomaly score should be proportional to something like that. And if your occurrence is kind of reduced, and so I'm not like, so this is your occurrences and this is your expected value, the difference like as it increases, so we can see that like our anomaly score should be proportional to that, and that should also increase. So for Midas, we use two things. The first is the streaming data structure. So we use sketches for this. So sketches are really essential for almost all streaming algorithms and all streaming or online algorithms. Sketches basically bring down like a high dimensional space to a lower dimension. And Countman sketch is one of the most popular sketch data structure. So we use two type of CMS or Countman sketch data structures. So in the first, like basically in the previous slide, we saw that we needed two things. So the first was an observed value, like getting an approximate observed value and an expected value. So expected is basically your total divided by your total time. So that is how you get a mean kind of value. And the observed will directly be stored in another data structure. So we see that like S is the approximate total count and A will be like storing the approximate current count, which is the observed count. And sketches basically give us like theoretical guarantees. So we have this A hat, which is less than equal to A plus mu NT. So don't worry about the details. So what it intuitively says is that with probability at least 1 minus epsilon, we can tolerate up to mu amount of error. So something like with 99% probability, we'll be able to tolerate around 0.5% error. So something like that, like a theoretical guarantee we get with sketches, using sketches. And like there's an Apache data sketches library, which is a really nice and open source implementation. So they've been doing like a lot of good work in this area. So feel free to check out sketches. And the other thing which we use in Midas is like combining the sketches with a chi-square test. So chi-square test is basically just a sum, like it is a very popular statistic, and we use like a summation over both the categories, the past and the present. And intuitively, like, so this is the score which we use in Midas. The derivation is in the paper. Like for implementations, I don't think it's required, but intuitively we can just see that A was the observed and S was the total, S by T becomes the expected, something like that. And our score is proportional to that. So that kind of can convince you. Like, so for details, you can definitely feel free to check out the proof and other things. So this is the final score, which we'll be taking into consideration and evaluating based on that. And so, like using these two things, this was MIDAS. So then we incorporate relations in MIDAS, which is the MIDAS R algorithm. So for incorporating relations, we incorporate two kind of relations, the temporal and the spatial relations. So temporal relations allow us the past also to kind of be incorporated into the current edge. So previously we saw we were just considering the current time instant. So instead of that, we'll be kind of considering the previous times as well with a diminishing weight. For example, if your current time was 10, time equal to 10. So we also considered time equal to 7, 8, 9, 10, something like that in a temporal relation with a reducing factor. So you consider time equal to 10 with like 100%, time equal to 9 with say around 50%, time equal to 8 around with 25%. So we diminish it by the same factor. Spatial relations in this, instead of just finding anomalous edges like just AUV, SUV, those were the data structures we were using. So instead of that, now we additionally have like SU, AU, and SVAV, so something like for source node and for the destination node. So we'll be able to see not just like count between two edges, but rather count coming out from a source node and like count of edges coming into a destination node. So based on that, then we'll finally take a maximum of all the three scores and give that as the score of the anomaly score of the edge. So like after MIDAS-R, so we also discussed the time and the memory complexity of both the algorithms. Like I mentioned, streaming or online algorithms need to have like a constant space and a constant like update time. And because we just use sketches which give like a lot of guarantees as well, so they are ordered W cross D space complexity, and the time complexity is ordered D. So W cross D because we have like D hash functions where every value is hashed D times, so that is the number of times it's hashed, and it is hashed into the W buckets. So we do some operations over the entire matrix, and that is how ordered W cross D. So now we'll be discussing briefly about the related work in this area. So anomaly detection in graphs is divided into static graphs and dynamic graphs. So for static graphs, we like for all the categories, there's an anomalous node detection, anomalous edge detection, and anomalous subgraph detection. So you can either detect like nodes, which nodes are anomalous, which edges are anomalous, which subgraphs are anomalous, something like that. There's been a lot of work previously in static graphs, but I think over the past few years, people have been trying to detect something like this in dynamic or time evolving graphs. And for dynamic graphs, there can be two kind of inputs. Like you can have a graph stream where you're getting a new graph at each time instant, or you can have like an edge stream. You're getting a new edge at each time instant. So an edge stream is at a finer granularity, and we were doing like detecting anomalies in this. So within edge streams, like our method basically lies in the edge detection category. And these were the previous state-of-the-art baseline Sedan Spot RHSs, and we compare with those in the experiments. So we also see that like these two baselines, they were also streaming algorithms and online algorithms. We'll see the performance aspects in a couple of minutes. But MIDAS detects microcluster and it gives guarantees on the false positives, which these approaches could not do. So now the experiments, we see that like we were basically using time evolving graphs, and any kind of graph can be used, but we use DARPA, which is a very popular intrusion detection kind of data set. So this is the conference version. We've also published like, on arXiv or recently a journal extension of this particular paper, where we have like a few more baselines and like a few more data sets. So for Twitter, we have like Twitter security and Twitter World Cup. So these were all tweet related graphs, but again, like I mentioned, we can use any kind of graphs, any kind of time evolving graphs. So just a small note here, like for Twitter datasets, like these are publicly available Twitter datasets, and for these, there were basically like tweets were extracted during these months in 2014 for security, like you had security related events, like there was a bomb blast or some other Ebola virus outbreak like, during that time. And for the World Cup, like the red card, like a yellow card, a goal is scored, penalty was given, something like that. So those kind of tweets, and we just saw like how our method and the baselines could compare with that. So some of these experiments are mostly, these slides are from DARPA dataset. So we see that like with like Sedansport got around 64% as the AUC, whereas Midas got around 91%. Midas are slightly improved upon Midas and it incorporated relations. So that went up to 95%. So the running times for Midas R, like we observed that Midas R takes slightly more time than Midas because it incorporates relations. But even then, like it like runs within less than a second. So DARPA is around 4.5 million edges. So this is on my normal MacBook. Like it runs within a second, whereas a DancePod takes up to like at least 2 orders of magnitude, like more time. And we also see like, so in the next journal extension, so we also see that like our implementations are slightly faster, and like we are at least 3 orders of magnitude faster than the previous baselines. Accuracy versus time. So this graph basically will be, we see that Midas and Midas are, they are around 2 orders of magnitude faster, and like they're performing up to 50%, like getting 50% more accuracy compared to the baseline. So that is just like a previous kind of graph itself. And scalability. So we see that Midas are, they're kind of scalable, and with increasing number of edges, the slope is like slope equal to one line, they're like lesser than that, and like almost like that is also like linearly scalable. And so then the real world effectiveness. So here we were considering the Twitter graphs. So on the right side, you see that like these are all the Twitter security related events. Like there was suicide bombing, a Gaza conflict, Ebola virus outbreak, and so along with that, these are like, so we plotted Midas R and Sedansport because of lack of space, but the peaks correspond to all these security related events which happened in 2014. So like for example, sixth peak is actually Mapletoni attack. So this is not plotted using the data. So this is an unsupervised algorithm. So we like, this is how like how well Midas was correlating with the ground truth events. Whereas if you see Sedansport graph below, so that is actually giving a high anomaly score for almost everything. So that is not really useful. We want a high anomaly score to correspond quite well to like our events, and we see that Midas could do that. So if we went into the details of this event 2 and 7, so we saw that 2 and 7 were not detected by Sedanspot. It gave a low anomaly score. Then we kind of analyzed 7 in more detail, and we saw that like this was actually a microcluster kind of anomaly, something like this, which was detected by incorporating the relation. So that was like a low priority event which Sedanspot missed, and I think even Midas missed it. But because of that, we incorporated relations, and we could see that. So MStream is the next extension of Midas. So in Midas, we were just considering two features like source IP and the destination IP. Now we've extended it to multiple dimensions, where we have like a higher number of dimensions, and like we have average packet size, flow duration, and these kind of things. So like it can be like basically anomalies earlier were just considered in like detected in just source and destination. Here it can be detected in event log data, record settings, or multi-attributed graphs where each edge has multiple attributes. The challenges for this work, MStream, were that like now we have to have analyze real valued features as well, because if you analyze this table, so 1000 and 995 have to be kind of similar, whereas 180 will be similar. Earlier they were all categorical features. And then we also did some like explainability in this, which part is anomalous, like what is causing the anomaly, and the correlation between the different features. And we also need to have like an added restriction here, that it has to be constant memory and time, both with respect to the stream length like previously, and like in addition to that with respect to the dimensionality as well. So MStream, like we've uploaded the paper on archive, and like the code is also available on GitHub, so feel free to check it out. So after MStream, like there were like a lot of discussion over GitHub, and like the repository became quite popular. People have been using it, so I definitely encourage all of you to also do that. And filtering MIDAS, the first one, like we've almost completed it, but that has come out of like all GitHub users. And because like one, I won't say a flaw, but one limitation of MIDAS was that we never really use our own detections to improve the algorithm further. So once we've detected something, even better if we can kind of filter that anomaly out so that it doesn't negatively affect the data structure. So that is what filtering MIDAS does, and we saw that the accuracy kind of jumped to 99% with that instead of 95%. So the code is uploaded on GitHub and it's updated, but the paper is another paper. So like you can check out my webpage for that. We can also have a parallel distributed or a GPU based version for that, because as we saw, like MIDAS gave a lot of speed ups, and like having a parallel implementation where you want to detect anomalies in parallel over several servers, that should be quite important for several applications and companies like Databricks and like Google and all these kind of companies. When you have multiple servers, you definitely want parallel implementation. So hardware implementation will also be quite uh, important similarly. And then there can be like an interesting search over how it performs on knowledge graphs and NLP settings. So I haven't tried that out with textual kind of graph data, but like that should be interesting if someone wants to do that. A periodic setting, so we haven't yet considered that. For example, like if you are buying something on Amazon, so you definitely expect that your average or your expected value kind of increases over, say, Christmas or Black Friday, something like that. So you cannot have like a constant kind of thing. So having a periodic setting and basically checking that out and like making adjustments according to that, we haven't done that yet. Apart from that, so like my original implementation was in C++. So in addition to that, like people have kind of implemented it in Python, Java, Ruby, Rust. I think like there were several other languages, but Erlang and Elfash aren't still done. But I think there are a lot of other languages. So you, like just you can even either contribute on GitHub or like check out the project, and like feel free to get in touch if you are remotely interested in anomaly detection, streaming anomaly detection, and if you want to like use it or deploy it in your settings. So we have like several other additions to this. Like we're trying to incorporate deep learning and like several aspects there, because streaming algorithms usually they're kind of considered separate from deep learning, but we're trying to see if we can kind of make a one pass and with like a small labeled data, like small set of labeled data, and can we use it to further enhance the performance. So definitely like feel free to get in touch if you want to collaborate in any way. And with that, I'll conclude. So the GitHub repository link is towards the right, the paper link is towards the bottom. And with Midas, we were detecting streaming microclusters in a streaming or an online manner, and we gave theoretical guarantees on the false positives. Also, Midas was shown to be effective over the baselines, like in a quite convincing manner. And yeah, with that, I'll take any questions you all have. Thank you.